Well, chemical rocket propellant uses the same, maybe that's a little bit too much. Chemical propellant uses the same mass that you're throwing out as your energy source. So you're limited by the amount of energy in the chemical energy. This gives you a maximum specific impulse of about 500 seconds. That is, you can have 1 pound of thrust on an engine, and it will run through 1 pound of fuel in 500 seconds. You'd like to get more out of it, and the only way to do that is have some other energy source. Unfortunately, so that's the good part. The higher your specific impulse, the more oomph you get out of your propellant. Unfortunately, it takes energy to do this, and this is the real problem. You're now putting energy, so you have an energy source somewhere, and that energy source needs to run on a power system. So here's an early example of a solar electric propulsion spacecraft. Notice the pretty big solar arrays. Here's an example of what a solar electric propulsion for Mars spacecraft might look like. It has an enormous solar array. The reason is because these ion engines in it, the electric propulsion engines, need power. Here's another concept. This was the old Jupiter concept. And notice, actually, it turns out the Jupiter concept here used a nuclear power system. And in fact, you might think, oh, a nuclear power system is so great, it doesn't weigh very much. In fact, this is the nuclear reactor, this tiny little thing down there. It turns out, however, all of the other stuff you need in a nuclear reactor is huge and heavy. In particular, it needs giant radiators because you need to convert that into electrical power to run the electrical engine. Electrical power runs by taking something hot, the nuclear core, and running a heat engine off of something cool. And of course, for something cool, you need a big radiator to keep it cool. So the proposed nuclear electric propulsion vehicles often look a lot like this. They have giant radiators, and that little teeny thing at the top is the actual nuclear reactor itself. So when people say, oh, nuclear reactors are tiny, well, that's partly true. But all the other stuff in the nuclear reactor is small. Well, let's see. I should talk a little bit about Vasimir, but I do want to remind people that Vasimir is just one type of electric propulsion, and there are many. So the Achilles heel for electric propulsion is you do need these power sources. You need a giant power source to, I'm trying to remember what slides I have. You need a giant power source in order to run any of these electric propulsion systems, Vasimir or any other one. But if you use that giant power source, you can get a lot out of your fuel. Well, is it good or bad? That's sort of the thing. Is it the silver bullet? It, to some extent, depends on what do we want to do in space. And let me give you 3 examples of things you might want to do in space. One, you might want to explore the solar system with robots. For this task, the electric propulsion systems are very important. They're very efficient because once we get out of the inner planets, if we want to go out to Jupiter, to Saturn, to the Kuiper belt, there's a tremendous amount of delta V, a lot of velocity change you need to get out to these systems. And the only way to do it without having enormous fuel tanks is electric propulsion. But oddly enough, Vasimir is a big electric propulsion system. For these missions with robots, we need smaller electric propulsion system. But there are such systems. These are the Hall thrusters, these are the ion engines, these are your standard magnetoplasma dynamic thrusters that, of course, all of you learned about in your advanced propulsion class in graduate school. These are the various other systems. So for robots in space, electric propulsion is great. Do we want to go to Mars? Well, if we just want to go to Mars, land on Mars, do a little science, come back, we probably don't need it. Because to use Vasimir, we need these giant, not only do we have to develop and test Vasimir, we have to test these large nuclear rockets. We have to get nuclear power in space, and it's kind of overkill. To just go to Mars, we can do it with chemical propulsion. In fact, Bob Zubrin's pretty much proved that. It's well known. So if we just want to go to Mars, explore a little while, come back, we don't need it. Here's a third thing we might want to do. Maybe we want to colonize the entire solar system. Maybe Mars is just a stopping point. We want to go everywhere. We want to go to Jupiter, to Callisto, to Mercury. We want to have a civilization that extends over the whole solar system. In that case, we probably do want Vasimir or something like it, because in the long term, we're going to need these nuclear power systems in space. Space is the place for nuclear power. If you're going farther away from the sun, there is less and less sunlight. If you're going into the comets, to the Kuiper Belt, to Saturn, you're going to want nuclear power. And you're going to want these highly efficient rockets that take a large amount of power. So the real question that we have to ask with Vasimir is, where are we going and what do we want to do? Is Mars the end, or is Mars the beginning of our exploration? It's a question for the people who want to know where we're going.
Okay. As I see it, the problem with a Vasimir is this. I mean, it's an interesting electric thruster. It has certain advantages and disadvantages compared to existing, more proven electric thrusters. But none of which, by the way, are remarkable, in fact. That is, compared to ion engines, which are much more proven, I would just as soon have one of them, but Vasimir, it can vary its ISP easier than an ion engine can. On the other hand, it needs superconducting magnets, which they don't, and so far its demonstrated efficiency of converting electrical power to jet power is only about 60% compared to 80%, which has been achieved with conventional ion engines. But peace. If Vasimir was simply a question of this is an interesting technology and should some money be allocated to work on it, I would have no issue with Vasimir whatsoever. I think we should have robust technology programs and promising ideas should be followed up. The problem is that it has been so hyped that it has been placed on the critical path towards humans to Mars. So that rather than becoming a tool that might be of assistance in the future, a possible addition to our toolbox, it has become a toll booth on the way to Mars. And furthermore, it won't deliver on the promise that it is currently making. That is, okay, look, the basic problem with any electric propulsion system, Vasimir, ion drive, any of the ones that Jeff mentioned, is that they require electric power. The amount of thrust is proportional to the amount of power, okay? But the mass of the engine also goes up as you increase the power, okay? So unless you can reduce the mass to power ratio, you can't increase the acceleration. Now, the actual largest space nuclear power system that has ever been flown is 10 kilowatts. That's a Soviet Topaz. And it had an alpha, the term Richard presented, which is commonly used, of 100 kilograms per kilowatt. That's reality. The Prometheus program that NASA had in about 2004 or so for the Jupiter mission hoped to get that down to 65. Now that program was aborted. It might have eventually achieved that goal. That's a credible goal, but it hadn't achieved it. But that's a reasonable target for space nuclear power systems. I think that if one is optimistic, quite optimistic, by the way, and also assumes a very large space nuclear power system to take full advantage of any promising scaling that you might get, and assumes a lot of advances in technology across the board, it could be reasonable to discuss an alpha of 20 kilograms per kilowatt. 3 times better, 3 times lighter than Prometheus hoped to achieve. But in Franklin Chang Diaz's mission analysis that he has presented in his various presentations, he assumes an alpha of 1 kilogram per kilowatt, okay, which is not possible. Okay? That's like steel with the weight of styrofoam. It's 2 orders of magnitude lighter than reality, and so it has no relationship to reality. If we could build things that light, we could not only have single stage to orbit like that, we could have single stage from Earth ground to Mars, okay, because we would have weightless propellant tanks and weightless spacecraft structures and so forth. It just doesn't have any relationship to reality. Now, electric propulsion, if you keep the power down, therefore the mass of the system remains low, even at realistic alphas of, say, 40, if you keep the power system small and go with hundreds of kilowatts, you can take advantage of the fuel saving available from high specific impulse and deliver cargoes to Mars with lower launch mass than is possible with chemical propulsion, but with a much longer trip time than is possible with chemical propulsion. So in the past and the present, many people quite credibly talk about electric propulsion as a potential cargo delivery system, which at the cost of significantly more complex spacecraft and various technology development would allow you to reduce the launch mass of a Mars mission. So you could send cargo that way. But it would take years for it to get to Mars instead of 6 months, which is what we could do with chemical propulsion or nuclear thermal rockets. However, Vasimir is being advertised as the way to achieve quick trips to Mars. And Chang Diaz says, well, all I need is 200 megawatts, which is also 200,000 kilowatts. And at an alpha of 20, which is 20 tons per megawatt, that means 200 megawatts weighs 4,000 tons. Okay, the typical HAB module that you might use on a manned Mars mission weighs 40 tons. So you're talking about sending a payload to Mars with an engine that weighs 100 times as much as the payload. Okay, we could deliver a 40-ton payload to Mars with chemical propulsion with a launch mass of about 120 tons. We could deliver it to Mars with an NTR with a launch mass of around 70 tons. Okay, but now we're talking 4,000 tons. And that's not only 4,000 tons you have to lift to orbit, it's 4,000 tons of highly expensive technology. It's not 4,000 tons of cheap propellant. Okay, so the launch mass becomes used, and furthermore, it doesn't get you to Mars in 40 days anyway, because I don't care whether you have 200 megawatts or 2 million megawatts, if the alpha is 20, the best you can do is get to Mars in 6 to 8 months. No faster than you could with chemical propulsion. So the numbers don't add up. And then finally, my objection to this, that is even deeper, is that this is being used by policymakers as the reason why we can't go to Mars today. Because we have to wait for this to come along. Okay, that is, we cannot go to Mars in 6 months because of the radiation. Untrue. The radiation dose in interplanetary space is only twice, dose rate is only twice that on the space station. And many space station astronauts who have done more than one rotation on space station or Mir have gotten radiation doses greater, cumulative radiation doses greater than they would going to Mars. In fact, if you want to know something, the space station program over the next 10 years, okay, the space station crew is 6, 7, about the same size as a Mars mission crew. Okay, it's going to be spending 10 crew years in space, equivalent to 5 crew years spent in interplanetary space. If we were sending human crews to Mars, every other opportunity right now with 6-month transit each way, okay, in other words, if the next decade we were sending missions to Mars, okay, every opportunity, 5 missions to Mars, we would be getting the same cumulative crew